Kepler, advanced business-driving AI at your fingertips.
The Kepler platform combines advanced automated machine learning, including deep learning, with easy-to-use, intuitive design, all within a framework engineered to help you scale AI across your business. Kepler can be used by anyone, with no machine learning experience required. Creating and implementing AI models into production happens in 3 distinct phases: data ingestion and exploration, model creation and evaluation, and model consumption. Kepler's automated data science workflows support users at every one of these stages. So let's start with data ingestion. First, I'm going to log in and navigate to the Projects section to get started. On this screen, I can see other projects I've created and also projects that have been shared with me by other users. When creating a project, I can add a name and description. This is useful when collaborating with others on the platform. Here, I have the option to share my projects with other users. Projects are private by default and are only shared with the users you define. This is a measure to keep your data secure. Kepler accepts data from multiple sources. You can add data from your local computer or a network drive. You can also connect the data that is in an Amazon S3 bucket, or you can query data with SQL from an SQL database. These connections are part of a growing list of connections that the Kepler team is rolling out regularly. Once my data is uploaded, I'm brought to the data validation screen that allows me to ensure my data is correctly formatted. Depending on the workflow selected, I am presented with a screen that allows me to adjust the formatting of the data as well as select my model target and its features. Below my category labels are pull-down menus that allow me to select from a list of data formats. Kepler will auto-populate these data formats. However, every data format is different, and I can leverage my knowledge of my data here to optimize the model. If I'm using a supervised machine learning workflow, such as classification or regression, I would be required to select a target for my model. A target in machine learning is the feature or category within my data set that I am trying to predict. For example, if I want to predict lifetime value, I would need to select the lifetime value column in my data as the target for my model. I can also select the features within my data set that I want to have included in my model. Features are the categories of data that may or may not support my prediction. I can use my knowledge as a domain expert to help optimize the model. I can select or deselect different categories to influence what parts of my dataset will be used to train the model. This stage is important. I need to think about the data that will be available at the time of prediction. All the features within my retraining dataset may not be present when the live data is passing through the model. Kepler will create the most effective, accurate model it can. If it can obtain a high accuracy with less features, then it will. I may upload a dataset with 50 or 1,000 columns, but Kepler may only need 3 or 4 to generate an accurate prediction model. And if those 3 or 4 variables are not present at the time of prediction, then my model will not perform as it should. Here I can deselect categories that I know have no bearing on the prediction, or in cases where I'm not sure about which features to include or omit, I can allow Kepler to determine this for me. Kepler features 8 automated data science workflows that fall into 4 main categories. The first category is classification, for tabular, text, and image data. Classification is predicting the class a data point belongs to based on the presence of similar variables. Prediction, for regression and time series forecasting. Regression is used to predict a future value based on the presence of other variables. Time series forecasting predicts future value based on the passage of time. Recommendation, user item recommender, recommends items and content to users based on the past purchase or consumption behavior of other similar users. Clustering, anomaly detection and clustering. Anomaly detection finds outliers in the data and groups them for analysis. Clustering groups both unlabeled and labeled data into distinct groups based on similar characteristics. Once you've selected a workflow and uploaded your data, training your model is a matter of answering a few short questions to help Kepler optimize your model. These questions are generated based on the data uploaded and the workflow selected. This is the final stage before Kepler begins training the model. To answer these questions, I'm only required to know about my dataset and my use case. No machine learning experience is required to build a working model. In training configuration, I can choose how many resources to dedicate to my use case. If I was prototyping or testing different datasets, I might want to choose basic. The basic setting is designed to give me a satisfactory result, but will run through a smaller set of possible algorithms, hyperparameters, and pipelines to generate the model. If I choose Advanced or Ultra, Kepler will consider more of these different configurations and pipelines, which will generally provide more accuracy at the cost of increased resources and model generation time. Below the resource selection area are questions that pertain to the data I've uploaded into Kepler. These questions vary based on the workflow I've chosen. The automated model training within Kepler is where it really shows its advanced machine learning automation. In conventional machine learning, this is where a significant amount of time is spent creating and optimizing models. During training, Kepler is generating a fully unique machine learning pipeline template based on my data. Typically, most machine learning platforms use pre-built templates that try to be a one-size-fits-all solution regardless of the data. But what's unique here is that these templates are generated using a complex decision tree method that analyzes my data and configurations, then tunes a template based on the features of my data. This generated template is what is used to optimize the algorithm and configuration process, which happens next. Kepler is now testing a series of different algorithms and configuration combinations in real time. In machine learning, when developing a model, algorithms need to be configured and tuned to optimize accuracy. This is typically a huge time sink for data scientists. However, in this case, Kepler is running through these combinations in a matter of minutes. These different combinations are then displayed on this leaderboard here, so as it trains, I can see which ones are providing the most accuracy. Kepler is also doing automated feature engineering. For algorithms that leverage deep learning, this is not necessary to use. However, in classical machine learning workflows, it uses advanced feature engineering, which looks at the various categories in my data and figures out which features in the data can be combined and created to generate a better result. Kepler is also handling the hyperparameter optimization, which, in machine learning, are the controls for the learning process. A lot of time is spent here by data scientists tuning these configurations to achieve the best results. When training is complete, I am presented with an evaluation dashboard. Each workflow has their own unique evaluation dashboard. This screen tells me about the performance of my model, as well as how my dataset was leveraged in the creation of the model. On the top, I have measures of the accuracy of the overall model. During training, Kepler splits the data. It uses part of it to develop the model, then uses the other part to test its efficacy. This is how it determines its accuracy. Just below that, there is the global feature impact. This tells me what features in my data are most driving the model's prediction. This is useful to know for many reasons. The first is in determining the logic behind the model. It's important to know what's driving the decision-making of the model prior to putting all of my trust into it. The second use of global feature impact is in generating insights. If my model is highly accurate, I can get general insights into what metrics I could be optimizing in my business on a process level. This information can be actioned outside the context of the model itself. Now below that, I have interpretability by sample. This functions similarly to global feature impact, but on a data point level. This will tell me what aspects of my data support or contradict the prediction on that specific data point. Not every data point will be the same. Some may have less information about them for the model to use in building its prediction. In some cases, Kepler may need to attribute a median value and apply more importance to another feature than the model normally would had the information been present. This is another level of transparency that allows me to understand what is going on in the background of the model. In this regression example, the left side of the evaluation screen shows the predicted values of each data point next to the actual value so that I can see how close Kepler is in its prediction. When I'm happy with my model, I can then put that model into production. Putting a model into production will mean different things depending on the intended use case. There are many ways Kepler accommodates this. The first being batch inference. Running batch inference is simply a matter of either uploading a new .csv or establishing another data connection. I can upload new data that I want to pass through the model and have Kepler output its predictions all within my workflow. I can export the predictions and start using my output in any way I see fit. For example, if I'm predicting customer lifetime value, I could take that output and provide that list to my marketing team and ad agency to develop highly tailored campaigns. If we keep with the lifetime value example, I could also take that output, isolate my highest predicted lifetime value customers, then load these customers back into Kepler. But this time, use our clustering workflow, where Kepler will group these high-value customers based on their inherent similarities to provide even more granularity for marketing teams to leverage in cross-selling and upselling. To the right of batch inference, we have online inference. Online inference allows me to essentially productize my machine learning model. I can add predictive capabilities to my existing systems by integrating my model via Kepler's API. This will enable data from these systems to pass through the model and deliver the output in a customizable way within those systems. For example, I can integrate an anomaly detection model into my industrial monitoring system to improve my anomaly detection capabilities. Or I can include a churn prediction model in my CRM system to flag customers at the highest risk of churning. Online inference opens up many possibilities to integrate machine learning models into multiple critical business activities. Models can be created and prepared for production in Kepler both quickly and easily. Leveraging powerful machine learning capabilities with Kepler means taking key aspects of machine learning projects from a timeline of weeks or months and putting them instead on a scale of minutes. What's more, this can be accomplished without a background in machine learning. Instead, you can use your knowledge as a domain expert to generate powerful, accurate prediction models that will change your business. This is the unique power of Kepler. If you have data and a use case you'd like to see demonstrated in Kepler, please reach out to us at strategy.ai/contact or sales@strategy.ai. Thank you.